Hello, everybody. We can start. Sundar, do you want to start?
Yes. So good afternoon, everyone. It's a great pleasure to all of us to introduce our next seminar, which is about electrochemistry. And my colleague, Gabriele Laudavio, is our speaker today. So I just wish to introduce him quickly. So Gabriele received his PhD in chemistry from Eindhoven University of Technology in 2020 under the supervision of Professor Timothy Noel. After a short postdoctoral stay in the same group, Gabriele then moved to the US and joined the research team of Professor Phil Barham at the Scripps Research Institute. So currently, Gabriele is acting as a university assistant at the University of Graz, and at the same time, he is also a key researcher at the Research Center Pharmaceutical Engineering, also in Graz. His current research is focused on the application of technology in the field of organic chemistry, with a special emphasis on the use of continuous flow chemistry and, of course, electrochemistry. So, Gabriele, the floor is yours.
Thank you so much, Shandor, for your kind introduction. And we are going to go straight to the slides. 1 second. I have to share the screen. Perfect. So, okay. So welcome, everybody, to this workshop. So today I'm gonna discuss with you a bit about what is synthetic organic electrochemistry and how can this technology be considered an emerging sustainable tool to implement to the formation and the synthesis of APIs and organic molecules of relevance. A bit of the agenda for today. So we will have the fundamentals of electrochemistry. We would do just an introduction on why electrochemistry can be important for us and what are the fundamentals that are behind this tool, this technology. Then we will briefly evaluate how can we exploit electrolysis across different scales. And then we will dive into some live or eventually real-world examples in terms of a very small scale, so electrochemistry applied to automation, high-throughput experimentation, and very large scale towards scaling up electrochemistry. But first, we will need to understand why is electrochemistry important, especially nowadays in our field, in the field of organic synthesis and generally speaking, fine chemistry. So we can see here, like in this picture, that there's like a desertic cliff, and on the other side, there's the promised land entitled sustainable organic synthesis, okay? So in the way we conceived and we have carried out traditionally organic synthesis, we have exploited the use of toxic and hazardous materials, stoichiometric oxidants and reductants with harsh reaction conditions, and most of the time we had to pre-functionalize our compounds to make them ready for the reactions that we wanted. But on the other hand, now we know that sustainability is very important and we should aim for better processes, better chemistry. And in this case, what we should aim for is something that comprises benign reagents and solvents, potentially skipping and avoiding stoichiometric oxidants and reductants using traceless redox mediators, such as electrons or photons. This would lead us to a milder reaction system. And most importantly, we can also develop methodologies that can use feedstock material as direct building blocks. But to do so, to bridge this gap, we can envision that the use of technological tools can help us in bridging this gap and provide a new way to get to a sustainable chemical manufacturing. Okay. So why electrochemistry? If we think about electrochemistry, it's defined in the IUPAC Gold Book as the branch of physical chemistry that concerns the relationship between an electrical potential and an identifiable chemical change. Now, this sounds very complicated, but what it means is basically that by applying our difference in potential in a cell, if we see any chemical change, we can consider this as an electrochemical application. And here I reported three of the, let's say, most important and commonly used ways to interpret and adopt electrochemistry in our daily base. So, for example, we have lithium batteries, which are very important. Every device, even the laptop that I'm using right now, is leveraging this technology, which basically provides electricity to our electronic devices. For example, here there's a facility for a chloralkali process, which is an electrochemical process performed at kiloton scale per year, where basically we are electrolyzing sodium chloride. But also the Hall-Héroult process is very important because it's the way we produce aluminum, metallic aluminum on large scale nowadays. So if we would like to funnel down the electrochemistry concept to organic synthesis, we can envision that electrosynthesis is the synthesis of chemical compounds in an electrochemical cell by applying a difference in potential. So we would like to observe the same identifiable chemical change as the IUPAC described, but for organic molecules. And why would we like to do that? In principle, one of the most immediate reasons that we can identify would be the replacement of wasteful, toxic, and hazardous reagents with traceless electricity. So instead of adding, for example, permanganate or lithium aluminum hydride to our reaction mixture, we can instead plug our cell to the grid, and we can let the electrons do the redox job instead of these chemicals. This obviously leads to a safer process because we will have less waste, we will have milder reaction conditions, and also we can avoid the use of, for example, pyrophoric reagents or very toxic carcinogenic compounds. Therefore, electrochemistry can be considered inherently sustainable and cost efficient in terms of like both waste management, but also chemical applications and so on. So the other opportunities that organic electrochemistry can give us is that by generating very reactive radicals, we can circumvent the use of other energies, let's say, other Gibbs energies to climb up the thermodynamic values and also to obtain the desired process. In particular, the use of single electron transfer reactions are most of the time is carried out at room temperature. So this is already a great advantage. And in principle, we can also see potential applications in terms of high throughput experimentation, the generation of library of compounds, and even to process scale up. And in this way, we can envision a cleaner, more selective, and more sustainable way of carrying out organic chemistry, generating our desired products. Okay, so now we can start diving into like the technicalities of synthetic organic electrochemistry, and everything passes through the use of an electrochemical cell. So in principle, there are two different designs of electrochemical cells that can be used. Everything depends on how we compartmentalize our reactions. So in the most common cell is an undivided cell where basically both the electrodes are submerged in the same reaction mixture, and they basically provide the difference in potential in the same media. On the other hand, we can also envision a cell design where the two redox events are somehow divided. Now, everybody in general chemistry saw these kind of cells where with a salt bridge that it's connecting them. For obvious reasons, in organic electrochemistry, since we are using organic solvents, that is very unpractical. Therefore, we prefer to use porous discs or membranes that allow the transfer of ions towards the two chambers without compromising the reactivity and contaminating our reaction mixtures with other compounds. Okay, so now let's start dissecting a bit how this cell works and which kind of components we need to have an electrochemical cell. In particular, we can envision systems where we actually make our own cells that would look pretty much like this. So we can use our own materials and we can connect them with crocodile clamps as it's here, and then we can use a simple steering plate to maximize the mixing of our reaction. And this is a very good, let's say, system for entry level. We can run our reactions in here, but reproducibility issues may occur because the electrode distance is not defined, and we may have problems in terms of replicating this across the world with different homemade cells. And for these reasons, lately we have commercially available standalone potentiostats that can allow us to run the reactions in a more reproducible way, and most importantly, everybody would share the same device, the same equipment, the same electrode materials, guaranteeing or eventually maximizing the probabilities of reproducibility and maximizing the efficiency of the processes. Okay, so these are more or less the designs that we can have. Let's start looking at the pieces of these devices. So the most important thing is the power supply, because in order to create a difference in potential between the two electrodes, so to start an electrochemical reaction, we would need something that creates these electron movements. And most of the time, actually all the times, this is a power supply. The power supply can be tuned in two different ways, as you can see in this dummy that I portrayed here. So we can have a system where the potential is controlled, and that's called potentiostatic or potentiostat. Or we can also control the current, and then at that point we have a galvanostat. In most of the time, these power supplies can do both. So it depends a bit on how, on which kind of reactivity we want to exploit or we want to scout. And for this reason, we can use these devices in both modes. The next part, which is the core of the electrochemical reaction, is where the electron transfer happens, and are the electrodes. So the electrodes, when we choose the electrodes, we have to take into account several important features. In particular, we always want something that is chemically stable, or eventually that doesn't get destroyed or molten or dissolved during our electrochemical reaction. And we want something that has also high electrical conductivity, and on scale, we also would like to have something that is cheap, or eventually that has a very long lifetime. Another parameter that it's very important to take into account when we are selecting the appropriate electrode material is the overpotential, which is defined as the difference between the half reactions theoretical potential, so the ones that we can find, for example, on tables in our textbooks or on Wikipedia, and the experimental redox event. So the potential that it's actually measured for the same transformation. There's a discrepancy between the theoretical and the experimental value, and this is reported for many of the common materials that we can find commercially available. And this is most of the time it's a parameter that dictates which kind of event is more, let's say, favored in the electron transfer process. So, for example, here we can see that platinum has a very low wear potential for hydrogen. So, in principle, the reduction of hydrogen is very favored for platinum, while that's not actually the case for mercury, where the discrepancy is higher. Okay. Then, obviously, the electrodes in an electrochemical cell are usually two, and they are the anodes and the cathodes. So for the anode is usually where the oxidation takes place, and we can envision two different scenarios where we want to use different anodes. So in the case where we want to have an oxidation in our reaction, the anode is going to be our working electrode. So we have to choose an electrode that it actually makes this reaction, allows this electron transfer towards the solution. In particular, the most common used material for research purposes is platinum, because it's very robust, it has a it's very durable, and it has a wide potential range that can be used. However, it's very expensive, as we know. So on scale, its use is prohibited, I would say, or eventually extremely discouraged. Another common material that can be used is the carbon-based electrodes, in particular graphite, which is very relatively stable, and it's extremely inexpensive. However, it can be eroded or corroded in very prohibitive oxidation conditions. Otherwise, we can use more robust carbon-based materials, which are, for example, glassy carbon or reticulated vitreous carbon, which is also called RVC. They are usually very hard, very robust, sturdy, chemically stable, but they are more expensive. In case we are not really interested in the oxidation part, so we would like, for example, to reduce our compounds, we can also choose anodes that get basically oxidized over time. So the metal zero gets slowly oxidized, and the ions are getting dissolved in the solution. These kind of electrodes are called sacrificial anodes, and they usually tend to be more reactive depending on their redox potential. So we can also kind of select the potential range where we work at based on the material that we are using. In terms of cathode, usually we can divide the cathode materials in two big categories. One is the one that has high hydrogen over potential. So in case we are not interested in reducing our H+ from acids, and we are interested in actually reducing, for example, organic molecules, we can use materials like carbon-based, so graphite, as I was saying before, or eventually tin, cadmium, zinc. These are all materials that are performing these reactions very well. In case we are, for example, more focusing on the oxidation, we can use the evolution of hydrogen as the counterpart of the reaction. And in that case, we can use platinum, nickel, or, for example, stainless steel. Another electrode that can be used in this kind of setups is the reference electrode. Now, reference electrodes are usually optional because they are commonly used in potentiostatic mode, so at constant potential. And generally speaking, these electrodes are nowadays we can purchase them. They are standalone, and they can just be submerged into the reaction media. In particular, there are the three most famous reference electrodes are the standard hydrogen electrode, the saturated silver chloride electrode, and the calomel electrode. Obviously, the calomel is now less and less used because of the involvement of mercury, which is toxic, as we know, and the standard hydrogen electrode is very complicated to use because we have to make sure that the hydrogen is evolving very well in order to keep the voltage stable to zero. So in organic synthesis, we are more prone to use these two electrodes instead. And for the reasons that I was saying before, usually saturated silver chloride is the one that is the most used. Another reason why we want to use reference electrodes is to record cyclic voltammetry analysis, which is basically a system, a 3-electrode system where we can evaluate at which potential the redox events take place. And in organic chemistry, this is widely used for example, for mechanistic experiments, so to evaluate where the electron transfer takes place, or to evaluate the reversibility of a redox event, to evaluate catalysis, but also to have a very precise potential where a reaction takes place. For example, in the synthesis of the xyamicin B, the authors have figured out that they wanted to make this nitrogen-nitrogen bond. They tried several chemical oxidants, but none of them was working fine. So they recorded a cyclic voltammetry analysis of the monomer, and they observed that they had a reaction like a redox event happening at around 1.2 volts. So by running this reaction in potential static mode at 1.2 volts, they managed to obtain the desired product. While if they were moving the potential, for example, to 1.6, they observed complete decomposition, showing that these systems, that cyclic voltammetry can be very useful also in a synthetic application. Okay, so now we evaluated the electrodes. Let's look at what happens in the solution. So the solution that we have to use obviously starts with the choice of the solvent. So the solvent in organic chemistry, in organic electrosynthesis, we have to balance between the solubility, so the solvents that can solubilize our starting material, but also they need to be good in transferring and moving the ions, okay? So for that, we rely on the physical parameter, which is called dielectric constant. And the higher is this parameter, the lower is the resistance of the cell. In particular, we can see that water, DMA, acetonitrile, they are good solvents for electrochemistry, while, for example, THF and DCM, they are not really good. Another thing that is very important to take into account during when we choose the appropriate solvent is the redox potential window. So it's easy to understand that every solvent will have a potential where it starts degrading, both from a reductive point of view or an oxidative point of view. So we have to choose a solvent that can operate within the redox potential that we would like to exploit. For example, if we look at DMF, it's very good at most of the redox potentials that are commonly used, while for example, acetic acid or water, they have limited application in terms of reductive potential. Okay, so what happens if we have a solvent that we would really like to use, a solvent that has a very low dielectric constant? In that case, what we can do to increase the ions present in the system and also lowering the resistance of the cell, we can use salts. So we can add salts to our solution to maximize our conductivity. In particular, in organic chemistry, the salts that are commonly used are tetralkylammonium salts, because they are bulky, they are relatively lipophilic, so they can be easily solubilized in organic solvents, but also lithium and in some cases sodiums can be used as cations. While for anions, we usually try to use non-nucleophilic anions, so bulky systems like, for example, hexafluorophosphate or tetrafluoroborate. Also, perchlorates can be used, but not on scale because they are explosive. And in particular, we have to take care of the dissociation of these ions. So it's also important that these ions get solubilized, so surrounded by solvent while they are in the solution. Then their ion pair is not sticking together in order to maximize our electrical conductivity. Okay, so to conclude the evaluation of the cells, we observed that it's the choices that we can make in terms of the design of the reaction vessel that we can use for synthetic organic electrochemistry rely mainly on the selection of the appropriate electrodes, of the cathodes and the anodes, the selection of the appropriate solvent, and the use of a supporting electrolyte. And in knowing this, now we can explore the physical fundamentals of electrochemistry. So in principle, electrochemistry is very simple in the way it's performed. So we have two electrons that are connected to the power supply, and we have a solution in between. When we turn on the power supply, what happens is that we create a difference in potential, and the electrons start moving from the anode, which is the plus, to the cathode, generating an accumulation of a negative charge on the cathode and a consequent positive accumulation charge on the anode. In this case, then we create a difference in potential, and the ions that are present in the solution start moving to form Coulomb attraction. And this basically leads to a system where we can navigate, or eventually we can steer the molecules towards the right electrode that we want to use, leading to a potential oxidation or reduction. Another thing that it's extremely important to notice is that the effect of the potential that we are using is actually what is impacting in the modification of our functional groups or our organic molecules. For example, in this graph, we can see that we can reduce, for example, alkyl or allyl halides at around -2 volts. Or, for example, if we have an oxidation, we can oxidize phenols at around 1 volt. So depending on the power that we use in the reaction, we can observe different kind of reactivities, and we can selectively choose which kind of reactivity we want to have in an electrochemical cell. Now, the last question that is left to discuss is which kind of mode shall we use for electrochemistry? So, for example, do we want to use constant current or constant potential? So for constant potential, as we just discussed right now, we can precisely control the redox events that are happening in the reaction. However, since the potential is capped, we can envision that the current is going down over time because the concentration of our starting material is getting lower and lower. So the reaction theoretically never reaches full conversion. And also, we require the use of a reference electrode in order to be reproducible, because the resistance of the cell varies from cell to cell. So if we use different cells without a reference electrode, we cannot select the same difference in potential. On the other hand, constant current, it's very reproducible because it's not really related to the setup and to the cell design. However, we sacrifice the precision of the reaction control because the potential may vary during the reaction, leading to over-oxidation, for example, or difference in redox potentials over time. For reproducibility reasons, in organic synthesis nowadays, we prefer to use constant current in order to maximize the reproducibility and the applicability of the reactions that we are designing. Okay, now we know the rudimentals of electrochemistry. We know how a cell works. We know how which kind of components the electrochemical cell is made of. Okay, but now let's dive a bit more into the organic synthesis part of this. So we may wonder, how can we translate electrochemistry to our day-to-day routine, so our day-to-day synthetic problems? And here I try to divide the different scales, how we can run reactions, and which kind of devices can be used to guarantee the reactivity from an electrochemical standpoint. Let's start with very small scale. So less than 1 milligram, we usually use this in, I would say, high throughput or medicinal chemistry systems where we make libraries, we create screening platforms. We want to have very quick reactivity assays. And for this reason, there are many HT well plate-like systems that can allow the use of multiple cells at the same time in one device. And we can use this also in other ways that we will see later in this workshop. But generally speaking, from a commercially available standpoint, we can use these kind of devices to have a sort of throughput experimentation for electrochemistry. Moving from milligrams to grams, we can envision the use of normal commercially available cells, and in this case we can do some we can apply this in the sense of drug discovery. We can accumulate enough material for biological assays. We can make the synthesis and evaluate synthetic methodologies, or we can even do, for example, late stage modifications. This is usually the place where medicinal chemistry operates. So when we are doing synthetic methodology development, this is usually the kind of designs of cells that we are employing. Then we can envision a transition from grams to kilograms, and here the common devices that are used for these applications are parallel plate reactors, or for example multi-rod batch reactors, where basically we have multiple electrodes connected in series. And a beautiful application of this is the synthesis of disulfone that has been successfully implemented by Merck US, and it has been done on a kilo scale using flow reactors. And finally, when we go across the kilogram scale and we start thinking in ton scale, we would go to the hardcore process chemistry up to the commercial process systems. And here I reported the two most known and famous synthetic applications on scale of organic electrochemistry, which are the synthesis of adiponitrile performed by Monsanto. And this is done in flow systems up to 300,000 tons per year. But also there are other scaffolds that have been synthesized. For example, from BASF, there's this intermediate towards lismeral, which is a fragrance. And this is currently done on around 20,000 ton scale. Okay, the reason why when we move from kilo, I would say from gram to kilo and then ton scale, from batch cells to flow cells, it's because basically we can merge the benefits of electrochemistry and flow chemistry to have systems which have improved mixing that can handle multi-phase reaction conditions. And usually, because the electrode gap is smaller compared to a large cell, we can also have, for example, improved selectivity, but also we can reduce the amount of supporting electrolyte, which is not always beneficial from a cost point of view. And in this sense, then we can envision a system where we move from very small system up to very large system, where we can use either big flow cells or eventually big tank reactors that are constantly recirculating, or a series of multiple flow cells in parallel. Okay, So now that I gave you an overview of what are the possibilities from very small scale to very large scale, I would like to introduce you two examples from very small scale and mid scale that we have performed in our laboratories in recent years. So one of the reasons why we want to do electrochemistry in small scale for high throughput experimentation is that usually high throughput is the bottleneck of high throughput is slow reactions. But in principle, electroorganic synthesis creates unique opportunities in that sense, because according to the Faraday law that it's written here, the reaction time in electrochemistry is proportional to the amount of material that we are electrolyzing. Therefore, we can envision that electrochemistry would be the perfect system for high throughput experimentation, because the lower the amounts that we are using, the shorter is the reaction. However, we are facing some engineering issues when we are miniaturizing electrochemical systems. So, for example, when we try to miniaturize batch reactors, we will have hard times in miniaturizing too much electrodes, because as you can imagine, if I have electrodes that are too small, they can bend, they can snap, and they are not robust anymore. This creates a lot of problems in terms of how small can I go in terms of an electrochemical cell. Also, this leads to not really Eppendorf or even smaller volume of reactions, and this obviously limits the amount of vials that we can have on a well plate. Or another big problem that we may have is that we need the constant use of glove box to ensure an inert atmosphere. When we think about miniaturizing flow reactors, on the other hand, we have the problem that running continuous flow reactions consumes a lot of material, and that if we run the reactions for too long, we may have problems in terms of electrode passivation and so on. So in our lab, we wanted to design a system that could circumvent and overcome these limitations. And for example, we wanted to design a system that could use very low amount of material by creating slug reactions, where our reaction mixture is segregated by two bubbles of gas. We wanted to use a very small reactor with only 64 microliters of reactor volume. And we also wanted to use a system that would allow us to have the product in single pass, so that would avoid recirculation, because that would take too long time. Ideally, this system would also be completely automated, because once we have a system like this, we can envision that there's a script that can orchestrate the entire platform and generate data autonomously. In this sense, we basically want to create a device, or eventually a platform, that has multiple modules, and then we can add them in a plug and play fashion to generate our desired high throughput machine. And so we envision a workflow that comprises a reaction mixture preparation and with a liquid handler, and that transfers the reaction mixture to the electrochemical reactor, and then we can have a sample collection. And for this system that has been developed in collaboration with Merck Darmstadt, we focused on the synthesis of half of the PROTAC fragments, where basically we were taking the glue and we were basically combining them with a linker by a nickel electrocatalyzed CN cross coupling. Okay. So we can see here how the platform works. We have the Python script controller, the reaction mixture preparation by liquid handler that is aspirating sequentially the reactants. And once the reaction mixture is generated, it transferred to the cell the electrochemical reaction starts automatically. And then basically once the reaction is done, the power supply shuts down, and then the sample is collected for analysis. And in this way, basically, we could run multiple reactions at the same time. And to validate the system, we took an amine that was working very well and one that was not working so well. And we tried the system up and down continuously for 20 times. And we could observe that the system was holding very well. There was no cross-contamination. And the average yield was almost the same over time. So there was no electrode passivation. Once we have validated the platform, then we move to create a library of compounds employing different amines that all of them or almost all of them have an exit vector that could be further scrutinized and used to attach the second part of the product fragment. In this case, we could observe that the reaction was working relatively well. We could also evaluate different trends, like, for example, the amine I wasn't working at all in this setting, and all the compounds were transferred from slug flow to continuous flow and isolated to obtain an amount of compound sufficient to go ahead with the medicinal chemistry campaign. Okay. In this sense, we also expanded the application of this platform, creating a closed loop system where also the analytics was done in flow and in an automatic way. And in combination with Bayesian optimization algorithms, we could create an autonomous platform that was generating autonomously optimizing reactions. And in particular, in this case, we wanted to overcome a complex multidimensional space for optimization with high molecular complexity. This is how the platform looks like. It's very similar to the previous one. So we had basically the same liquid handler, the power supply, the pump, the reactor, and then we added a 6-way valve to compartmentalize the ambient pressure system to the high pressure that was going directly to the UPLC analysis. And in this case, we took over from where we left. So we did, again, this CN electrocatalyzed cross-coupling. And we ran our Bayesian optimization where basically the new reaction conditions could be identified in terms of optimization. We isolated the compound by scaling up these conditions. And also we could observe very interesting trends based on the Bayesian optimization campaign. For example, we could identify the optimal nickel amounts or the optimal current that should be used and so on. Okay, so this is pretty much a story about very small scale. Now let's assume that we have our reaction and that we want to scale it up to, I don't know, decagram scale. How can we do it? In our lab, we have recently developed a system for hydrocarboxylation reactions using CO2, where basically we have used a spinning cylinder electrode reactor, where basically one of the reactors is rotating and acting as a steering element in the system to generate these hydrocinamic acids, which may have applications in the fine chemical and also the agrochemical space. Basically, we started by optimizing the reaction in the ICA electrosyn cell until we optimized and we obtained around 70% yield. And then once we were satisfied with the batch optimization that was using a large excess of CO2, we moved to the spinning electrode reactor. And in this case, we managed to control the amount of CO2 in order to have a limited amount of equivalence and obtain the product with the higher yield at higher scale, because this is 50 milliliters compared to the 3 milliliters of the batch. Another important thing that we observed here was that by adjusting the current density, we could also obtain different selectivity in terms of like hydrocarboxylation, anti-Markovnikov or Markovnikov. And this is due to the unique combination between high mass transfer and the high current density. We obviously also scale this reaction up to in recirculation mode, where this is like the reservoir, and this is our reactor that is submerged into a liquid to keep the temperature stable. And we could obtain a productivity of 50 grams per day, and we run the reaction at around 20 gram scale. Okay, so this leads me to the end of this workshop, and I hope that I could demonstrate to you that electrochemistry can be a gateway for new, not only new and exciting chemistry, but more importantly for new opportunities in terms of sustainability and green opportunities in terms of like translating old methods and all protocols to obtain blockbuster molecules and APIs in a more benign fashion, thanks to the unique capabilities of the single electron transfer of electrochemistry that can allow the removal or the circumventing the use of stoichiometric oxidants and reductions. In this case, we envision that we can expand the chemical portfolio to generate new ways to make compounds in a greener and greener fashion. With this, I am done. I want to thank you for your kind attention. And if you have any question in the chat, I would be more than happy to discuss them with you. Thank you.
I think we do have, so thanks, Gabriele. We have a question from Christian. You have a question first.
Yeah, I start off with a question. So thanks, Gabriele, for an excellent presentation. I learned a lot about electrochemistry in synthetic fashion. I have a question with regards to the proper choice of electrodes. So when it comes to surfaces, yeah, there is lots of surface effects that may influence the reactivity or the kinetics of a reaction, of a transformation. How much are surface morphologies responsible for reactivities, but also for selectivities in reactions, and how much are they taken into account for the choice of a proper electrode in a electrochemical reaction?
Yeah, a very good question. I would start with your last question first. So the choice of the electrode, it really depends on your reactor design. That's very important. So for example, in organic synthesis, when we use parallel plate reactors, we try desperately to avoid foams and the tridimensional structures. We prefer to use plates because in this way, we avoid stagnation of the reaction mixture. We can all, I mean, foams can be used in flow-through reactors where we are basically inputting the reaction solvent through the electrode, but that can create a lot of problems. So usually we used to use like plates where we have a very defined flow path, and in this sense, that's better or eventually easier to operate, I would say. When it's about batch, the three-dimensional structure is something that we cannot ignore. On the other hand, though, I would say that the most important thing is the combination between the current density and the surface, because that's where the magic takes place. So the current density has to take into account the surface that you are using, and that can be very complicated when we are using foams or, for example, carbon felt, especially because these kind of parameters are usually not available from the providers that sell this kind of things. So it has to be measured by inside, I would say, by the insiders, but who buys these things, and it can be very complicated. But generally speaking, in terms of organic electrochemistry, by experience, I can say that the reactivity is mostly ruled by the nature of the electrode rather than the structure of the electrode. So, for example, if I have a metal electrode, I can expect certain reactivity. If I have a carbon-based electrode, I expect different reactivity. And generally speaking, they are aligning relatively well, unless you have a very weird reaction. That can always be the case, but relatively simple reactions, they always tend to behave the same if I have a metal, regardless of if it's a foam or a plate, and the carbon the same. The only thing that can change maybe sometimes is the selectivity or the mass balance, but that is again more due to the current density rather than, so the impact, the dual impact of current and three-dimensionality rather than the three-dimensional structure itself of the material.
My question, thank you very much for this explanation. My second part of the question was more related to, I mean, the three-dimensional structure, not in terms of shape of the electrode, but rather on the molecular scale. If it's more a porous material or a polished, very flat electrode. So how does the porosity, the surface morphology of the electrode play a role in the chemistry? Is there anything that is taken into account, like if I remember the difference between a polished platinum electrode versus a shady platinum electrode? There is certain differences in reactivity. How much is that taken into account when it comes to other metals?
It's definitely taken into account, I would say. So generally speaking, in order to simplify as much as we can the chemistry in organic synthesis, we try to use compact and flat materials in which the intercalation or the tridimensional structure is not really impacting, and the reason is because we want to avoid this kind of scenario. Sometimes, especially when you use organic solvents and graphite, if you use a graphite that is too soft, the solvent can intercalate between the graphene sheets, and then we can get into insulations, or eventually the reaction stop working for a random reason. So you have to imagine that in terms of pencil hardness scale of the graphite, usually we go from 5H above. So this is very, very, very hard graphite. So very compressed in order to avoid any space that can be created. For metals, it's easier because obviously, I mean, it's much more compact material. Also in that case, I would say flat material, it's easier to use, especially because you have to polish them in the end. So between one reaction and the other. So inevitably, even if it has a very fancy three-dimensional structure, like for example, platinized platinum, just saying one, when it's about cleaning it up, you would lose that beautiful three-dimensional structure. So cleaning is a very important part of electrochemistry, and I'm very glad that most of the journals nowadays are aligning in guidelines of like not only the reaction itself, but also the cleaning procedures of the electrode has to be embedded into the general procedure, because this is something that at the very beginning has overlooked, and it has created a lot of problems in terms of reproducibility. And ideally, we live in a world where we want to use our electrodes for an infinite amount of time. So we don't want to use them as disposable, especially when we are using, like, for example, I don't know, gold or platinum or I don't know, silver electrodes. So that's also the reason why we try to keep it as simple as it gets and use simple plates, I would say.
Okay, thanks a lot.
You're welcome.
All right. So we have still a couple of minutes left, and there are a few questions on scalability or challenges faced for the upscaling. So maybe you can elaborate on that, Gabriele. So what were the biggest challenges that you faced during scale up?
That's a very good question. Obviously, I think that we have reached already a point in electrochemistry where we are ready to the leap of this technology from a research scale to a scale up. I have the feeling that there will be more and more research and success in the future in this area. So the largest scales that we have run in our reaction are, I would say, 100-gram scale, 200-gram scale. That's the largest scale that we have run in the lab, obviously, because on a research lab, it's very hard to scale up further, because then we were already using 90 ampere systems. And as you can imagine, these amounts of current density in presence of organic solvents without the appropriate safety assessment can be very dangerous. So we don't recommend to go to super large scale on a research lab setting. And that's also the reason why we personally scale this up to maximum 100-gram range. Can be scaled up much further, but for us, it's more a proof of concept rather than a proper, industrial commercialization or application. What are the challenges? Challenge number one is dilution. We have to try our best to maximize the concentration. And that's already a very big challenge in organic electrosynthesis. Number two is the use of supporting electrolytes. So we have to, in a way or the other, step away or minimize the use of organic supporting electrolytes as much as we can. Ideally, we would love to use like sodium chloride as electrolyte, because that's very cheap and it's completely safe and it doesn't impact the environment. And I see also that there's a comparison with photochemistry. Well, I always saw photochemistry and electrochemistry as very complementary in the things that they can do. I think that electrochemistry is more ready in terms of higher scale up. So I would say like production scale, because electrochemistry has been already very well exploited in the organic chemistry world on multi-ton scale. Like Halle-Rowe process has been done like million-ton scale per year, okay? And that's electrochemistry. So we have already the reactor technology that can be translated from inorganic to the organic world. And all the regulations can be copied one-to-one. We just have to like adjust that to organic chemistry safety and hazard. For photochemistry, it's more complicated for many other reasons, and one reason in particular is the heating of the high intensity lights that have to be sunk out, and that has to be included in the cost calculation of the energy input output, which is something that has not been exploited very well yet.
Yeah. All right. Thanks a lot, Gabriel. I see it's 3:00 now, so we need to wrap up here. So thanks a lot for this very, very enthusiastic and very informative session you gave us on electrochemistry. I hope for the audience it was very informative as well. There are still some open questions. We will take them offline. So Dirk, no worries, the answer will come to you in terms of safety. But I suggest we close the webinar here, and thanks a lot to Gabriele and of course the audience attending here. So hopefully see you next time in our next webinars.
Yeah, also feel free to reach out to me in private if you have any curiosity or specific question. I will be more than happy to help you out with that.
All right. Perfect.
Thank
See
you.
you.
Thank you.
Ciao.
Bye.
Bye.